for not giving the same talk like announced in the program. Just because I thought I sent the new title, but I didn't. But I believe this talk maybe is a bit lighter and will be more entertaining. And also it is about the Minimax theorem, which is certainly useful both in learning theory and as well as in lower bounds, the average case lower bounds. So I believe this is relevant nevertheless. Okay, I see some people are still coming in. Okay, so we'll slowly. And then another advantage is that this is a joint work with Steve Haneke and Roy Livni, and Roy Livni did make it to the workshop, and you can ask him all the questions you have later.
If I remember what we did.
Sorry?
As if I remember what we did in that work, and I remember. So now you put me in a position when I need to read the paper.
Yes, that's okay. So let's begin. So let me start with some background. So last year we were trying to prove a statement about online learning, and we managed to do that. We found a proof which is based on the Minimax theorem, and consequently our proof did not apply in the most general case, infinite hypothesis classes, abstract, in the most abstract case. And this is not uncommon in ML theory and maybe even in computer science. And usually you just sweep it under the rug. So let me give you a couple of examples. So this is from the paper that introduced the VC dimension to the West I forget all the name of the authors, but Manfred Warmuth, Hausler was there. Who else? I don't remember all of them, but let's read it. So after Vapnik, we will adopt a naive attitude toward measurability, assuming that every set encountered in our proof is measurable. Okay, so you take the minimum sigma algebra that contains all the set definable by the paper. Here's another one from another paper. In learning theory, some of our arguments exploit the Minimax theorem for zero-sum games. Therefore, we will assume a setting in which this theorem is valid. Alternatively, one could state explicit assumptions such as finiteness or forms of compactness, under which it is known that the Minimax theorem holds. However, we believe that the presentation benefits from avoiding such explicit technical assumptions and simply assuming the Minimax theorem as an axiom in the discussed setting. This is, by the way, from a paper of mine. I wrote this paragraph. Okay, so sometimes indeed it makes sense to lose generality in order to simplify presentation and focus on the key and novel ideas. But the result we'll discuss today was discovered while attempting to generalize the result beyond what was needed.
Sorry, Shay, can you hear me? Can you just explain what is the issue here? So you're saying the Minimax does not apply in general?
I will explain this in more. I will explain it soon in much more detail. Don't worry.
Okay. All right.
This is just the background. But what I want to say is that so we really extended the result way beyond what was needed to be accepted to the conference. And what's interesting is that this side result we came up with turned out to be much more popular than the main result of the paper, and even among the conference people. So abstract nonsense sometimes is nice. That's the takeaway. Okay, so let's now discuss the Minimax theorem, and I think this will also address the question that I believe Igor just asked. I cannot really see, but okay. So the Minimax theorem. Let's start with the way von Neumann thought about this theorem. So as far as I can see, there could be no theory of games without that theorem. I thought there was nothing worth publishing until the Minimax theorem was proved. So what is the Minimax theorem? Let's recall this. So we have what is a game? Okay, so we have we assume we have two players. We call them Mini and Max. Each of the players has a set of pure strategies, and these are just abstract sets, but you can model with it any game that has two players. And there is the rules of the games, which are encoded by this payoff matrix, right? So for every pair of strategies, one strategy for Mini and one for Max, the payoff matrix specifies who is the winner. So if M of S and T is 1, then Max wins. So Max wants to maximize. Otherwise, if it is 0, then Mini wins. Right, so we assume here a combinatorial setting. So there is a winner and a loser. It's not real valued. It's really combinatorial. And we also allow them to use randomness, right? So Mini and Max can use randomized strategies. So Mini can pick a distribution over pure strategies, and Max can pick a distribution over his pure strategies. And we extend the payoff matrix to randomized strategies in the obvious way, right? So we just take an expectation over two independent random draws from the mixed strategies, and we look at the expected value of the winning indicator. Okay, I guess this should be familiar to most of you. Okay, so what does the theorem, what does the Minimax theorem tells us? It tells us that if S and T, if the sets of pure strategies are finite, then this equality holds. So the minimum over P of the maximum over Q of the value is equal to the same expression, but in reverse order. So the maximum over Q of the minimum over P of the same value. And let's try to interpret it. So in the expression in the left-hand side, the mean P max Q, we can think about it as if first Mini picks P, first Mini declares her strategy, then Max, knowing P, picks his strategy, and then they play. So Max has an advantage because he knows which strategy Mini picked. And in the reverse order, Mini has the advantage because she plays second. So what the Minimax theorem tells us is that it doesn't matter who plays first. If for every strategy of the opponent, there exists a response that wins with probability at least V, then there is a universal strategy such that no matter what the opponent plays, I'm still going to win with probability at least V. Are there any questions? Okay, good. So so let's introduce this definition. So whenever we have a game that satisfies the Minimax theorem, we define the value of the game to be this the common value of these two expressions. Okay, so this is the value of the game. Okay, great. Now, here is the question that we study. Does the Minimax theorem apply to infinite games? So, first of all, it is not hard to modify the standard proof for the Minimax or to observe that actually it applies even if only one of S or T is finite. So if only Mini or Max have a finite set, then the Minimax theorem applies. And there are various other extensions that assume a geometric or even a more abstract topological structure, and they replace finiteness by compactness. So the most general form, I think, is Sion's Minimax theorem. However, there are very simple infinite games for which the Minimax fails to hold. It doesn't hold. And the next thing we'll do is we'll see such a game which was popularized by Ephraim Kishon. Ephraim Kishon is a Hungarian-born Israeli satiricist, so he wrote very funny short stories. and he defined the game that we're going to discuss. So let me define it by reading a part of his related short story, and I recommend all of you to read it at your free time. It's available online. Okay, so let's read it. So for quite a while, the two of us sat at our table, wordlessly stirring our coffee. Ervinke was bored. All right, he said, let's play poker. No, I answered, I hate cards, I always lose. Who's talking about cards? I was thinking of Jewish poker. He then briefly explained the rules of the game. Jewish poker is played without cards, in your head, as befits the people of the book. You think of a number, I also think of a number. Whoever thinks of a higher number wins. This sounds easy, but it has 100 pitfalls. All right, I agreed. Let's try. We plunked down 5 piasters each, and leaning back in our chairs, began to think of numbers. After a while, Ervinke signaled that he had one. I said I was ready. All right, let's hear your number, said Ervinke. 11, I said. 12, Ervinke said, and took the money. I could have kicked myself because originally I had thought of 14, and only at the last moment had I climbed down to 11. I really don't know why. Listen, I turned to Ervinke. What would have happened had I said 14? What a question. I'd have lost. Just the charm of poker. You never know how things will turn out. But if your nerves cannot stand a little gambling, perhaps we had better call it off. Without saying another word, I put down 10 piasters on the table. Ervinke did likewise. I pondered my number carefully and opened with 18. Damn, Ervinke said, I have only 17. I swept the money into my pocket and quietly left out. Ervinke had certainly not dreamed that I would master the tricks of poker so quickly. He had probably counted on my opening with 15 or 16, but certainly not with an 18. Ervinke proposed to double the stakes. As you like, I sneered, and could hardly keep back my jubilant laughter. In the meantime, a fantastic number had occurred to me, 35. Lead, said Ervinke, 35, 43. With that, he pocketed the 40 piasters. I could feel the blood rushing into my brain. And it continues, and it's a very, very nice story. Again, I really recommend reading Kishon's. He has very good, very nice short stories like this, and yeah, it can improve the mood sometimes. Okay, so let's now present this game in our language, in mathematics. So the sets of pure strategies for both players, for Mini and Max, are the same. These are just the natural numbers. And the payoff matrix is this infinite diagonal matrix, right? So whoever has the larger number wins. And Kishon didn't specify what happens on the diagonal when they pick the same number. So we just assume that any assignment of 0 or 1 to the diagonal will also be called a Jewish poker in our definition. Okay? Now, notice that the Jewish poker does not satisfy Minimax, right? So let's take a second to see that. So what happens if Mini plays first? So she declares her strategy, her mixed strategy, which is just a distribution over the natural numbers. But then Max, knowing this distribution, can pick a number far away in the tail of this distribution and guarantee that he will win the game with probability as close to 1 as he wants. Right? So if Max plays second, he can guarantee the value that he can guarantee of winning is as close to 1 as he wants by picking numbers far away in the tail of the distribution. And because the game is symmetric, Mini can do the same thing if she knows what Max has played first. So we see that there is really a big difference who plays first. So Minimax doesn't apply to this game. And the main result, or not the main result, the side result in our paper was that this, in some sense, Jewish poker is the only obstacle for the Minimax. So let me be more formal. So let M be an arbitrary, possibly infinite, uncountable, no restrictions whatsoever, no structure, no geometry, no topology, just some game with values in 0 and 1. Then, if the payoff matrix does not contain arbitrarily large triangular submatrices, then the Minimax is satisfied. Right? So, and contains a submatrix series up to permutations of rows and columns. So really, so contrapositively, what this says is that if the Minimax theorem fails to hold, if you found a bad game that doesn't satisfy the Minimax, then you can find arbitrarily large subgames of Jewish poker in it. Okay, so there is a certificate in a form of an arbitrarily large subgame of Jewish poker for not satisfying the Minimax. Now, I hope to tell you something about the proof, but before that, let me present a couple of open questions. But even before that, let me take questions if anyone has.
Does it mean that it contains an infinite submatrix or an arbitrary? Or for any size, you have a matrix of size bigger than?
The second, the latter, so this is my first open question, or I even dare to say a conjecture, is that we can strengthen this theorem by saying that the Minimax applies even in the case when there are arbitrarily large submatrices, but there is no infinite triangular submatrix. So this is a conjecture. We don't know how to prove this. And we proved the weaker form of this conjecture. So we proved that if the payoff matrix does not contain arbitrarily large triangular submatrices, then the Minimax theorem applies. So this is indeed this answers your question, right, Avishai?
Yeah.
Good. Yeah. So again, about this conjecture, we can think that if the Minimax theorem fails to hold, then simply it means that Jewish poker is a subgame of our game. Okay. Another, it's not really a formal question, it's more like a meta question, is whether there is a finite manifestation of this theorem that we just presented. So is there a sense in which finite games with no large triangular submatrices satisfy a more efficient version of the Minimax? Maybe efficient, so you can plug in for efficient and the large, you can interpret it in many ways, but one very natural way is that computationally, so efficient in terms of computation. Maybe you can compute an equilibrium for such games faster, or yeah, I don't know. So this is more of a meta question. Okay, and if there are no, so are there any other questions? Otherwise, I'll try to say something about the proof.
I kind of have a hard time thinking. I mean, how can there be an infinite matrix that does not contain very large triangular submatrices? I mean, it seems like I don't know. Can you give an example? I mean, it seems like you can always pick some rows and columns to get something triangular.
Take the infinite identity matrix, right? It will not contain.
Okay, but that's not terribly interesting.
Any
Okay.
symmetrical matrix, right?
What's that?
Sorry?
Any symmetrical matrix?
Any symmetric metric? I'm not sure. No, not sure. Any symmetric metrics will not contain because you are also allowed to.
The rows and the columns don't have to be the same. That's right.
I guess maybe can you give us a game, an infinite game on which you can prove a Minimax? Maybe that will give me a sense what.
I don't know if there are, I mean, take any, of course, any finite game satisfied. You can just continue with zeros, but you can just think about it as a collection of subsets, right? So each row corresponds to, let's assume the domain is natural, it's a countable matrix. So each row is just a subset of natural numbers. So you want an infinite family of subsets of the natural numbers that doesn't contain an infinite chain when projected to. That's what it says, right?
Yeah. Okay.
Okay, so you want to, so any, like anti-chains, like anything like that will be, so combinatorially we can describe it easily, but if, whether I have a natural game, yeah, I don't know, I need to think about it.
Okay, thanks.
Any other questions? Okay. So let's how much time do I have, by the way?
Maybe 20, 25 minutes.
Ah, great, awesome, great. Okay, so let's try to describe the proof. So this is again the theorem. So let M be any game. So we can think about like this countable matrix if you want. Then if the payoff matrix does not contain arbitrarily large triangular submatrices, then the minimax equality applies. And the proof will be as follows. So we will assume towards contradiction that there is a game M that does not satisfy the minimax, yet the largest triangular submatrix of M is of bounded size. Let's say 100 by 100. Okay, so we assume a counterexample for this theorem. So it does satisfy the minimax, but it doesn't contain triangular submatrices of size larger by 100. And we will reach a contradiction to item 2 by showing that M in fact contains an infinite triangular submatrix. So we will actually show that M contains Jewish poker as a subgame. Okay, so this is the strategy. We implement this strategy using 2 lemmas. So the first lemma, which we will prove now, tells us that you can find sequences of sets of strategies. So S1, S2, S3, these are subsets of strategies of mini. And T1, T2, and so on are subsets of strategies of max. And all of these subsets are finite and uniformly bounded by some integer D. And the value, when you let Si, when you look at the game induced by letting the strategies in Si against the strategies in Tj, so this is a D by D matrix. So the value of this game is above some threshold R or below some threshold R, depending on whether I is lesser or greater than J. Okay, so this will be the first step in the proof, and in the proof of this lemma, we will use the uniform laws of large numbers. So it's like a fancy union bound. And the second lemma is that if we have such sequences of sets of strategies like promised to us by lemma 1, then there is a choice function. We can choose small si from big si and small tj from big tj, and the subsequence of the integers k1, k2, and so on, so that the metrics induced by these by the SIs in these indices and the TJs on these indices is exactly Jewish poker, is an infinite triangular submatrix. Okay? So you can think about it that in lemma 1, we get this kind of a list version, set version of the minimax, where we have this threshold R, and then we have a choice function that actually rounds this to a minimax. And the lemma 2 uses uses Ramsey theorem. This will give us the choice function. And one nice fact that I learned is that Ramsey theorem and the Minimax theorem were proven in the same year, in 1928, almost 100 years ago. Okay, so let's sketch the proof. Any questions about these lemmas? Is this okay? Good. So let's prove lemma 1. So in lemma 1, we want to produce these sequences of sets of strategies of size D. So remember that we assume that M does not satisfy the minimax theorem. So by assumption, if you take inf P sub Q, you get a larger number, beta, than if you take the opposite, sub Q inf P, right? So if max plays second, it can get a higher value than if mini plays second, right? So I already tell you what is going to be this threshold here. It's just going to be the average of alpha and beta. Okay? And now we need to produce this sequence of sets. And we do it by induction. So we construct them inductively. So assume we already produced S1 up to Sn and T1 up to Tn. And now we want to construct Sn plus 1, and we do it as follows. So consider the game where max pure strategies are restricted to the union of the TIs. Okay, so mini is not restricted. She can pick any strategy from capital S, which is infinite, but max is restricted only to the union of the TIs. What can you tell me about this game? So in this game, we know that max has a finite set of strategies because each TI has size D, so the total size is n times D. So this game satisfies the minimax, and hence it has a value at most alpha. Why at most alpha? Because mini here has an advantage, and she can guarantee the better value, which is at most alpha. She is not restricted. Therefore, because the minimax is satisfied, so there exists some universal strategy for mini, such that for every strategy of max from these n sets of strategies, this mixed strategy of mini guarantees winning probability of at least 1 minus alpha, or the winning probability of max is at most alpha. And so we have this randomized strategy for mini, and remember, what we want to do now is produce Sn plus 1, which is a set of pure strategies. So what we're going to do is to simply sample, right? What is a randomized strategy? It's a distribution over pure strategies. So we're just going to sample from these mixed strategies. So Sn plus 1 is derived by sampling strategies from P, and P is guaranteed to us from the minimax. And in particular, it is enough to sample the VC dimension of matrix. It's not important to know the definition of the VC dimension over the beta minus alpha squared. Okay, so this is just a number that arises from a calculation, but I do want to say something about it because, okay, so what do we know? We know that if you fix some strategy from the B from the union of the TIs, we know that P, a random strategy from P in expectation achieves value of at most alpha. This means that if you take, by Chernoff, if you take log 1 over delta over epsilon squared, and you look at the average strategy of the strategies that you sampled, then with probability 1 minus delta, it will give you a value of at most alpha plus epsilon, right? By just a simple Chernoff bound. You just sample, you use the fact that when you sample from P, then for a fixed strategy B, you win it with probability, or you lose to it with probability at most alpha. Then by Chernoff, if you sample many independent copies, then the average of these copies is going to lose the probability at most alpha plus epsilon. And epsilon delta are derived by Chernoff. Now, what we want to do here is to apply union bound, right? We want to show that there exists a good sampling from P that holds simultaneously for all the strategies in the union of the TIs. But the issue is that there are many strategies there. There are n times D. And we want to just have these strategies, not a function of n. And this is where what I told you before, the fancy union bound comes into play. So in particular, here we use the assumption that the matrix M does not contain a triangular submatrices of more than 100 by 100, or 100 is just a constant, right? And therefore, the VC dimension of this matrix is small, and then VC theory, and I don't want to get into it, allows you to do this fancy union bound and to just and to get a number of samples that is independent of the union of the TIs. So okay, for those of you who are not familiar with VC theory, just notice that here there is a subtle point, but this subtle is quite standard. This point is quite standard. It's nothing very yeah. It's a standard argument. Okay, and Tn plus 1 is derived in a symmetric manner, just in using the same argument. Okay. So now let me explain how we derive the second lemma. So let's first recall what it says. So now we already have this S1 up to these sequences of sets S1, S2, and so on, and T1, T2, and so on. And now we want to reason that there is a way to choose a pure strategy, a sequence of pure strategies such that the obtained game is a Jewish poker, is infinite triangular. So let's do it. So we're going to use here the infinite version of Ramsey theorem. So let me first tell you what it says. So the infinite version of Ramsey theorem, we look at an infinite graph. Here the vertices of the graph will be the natural numbers. And we have a coloring of the edges, right? So we have a clique over the natural numbers, and we color each edge in this clique, but from a color among finitely many colors, right? So we have maybe 20 colors, and we color each edge by one of 20 colors. So the infinite Ramsey theorem will tell us that there will be an infinite subset of the vertices, which is monochromatic, such that all edges have the same color. So this is the theorem we're going to use. So in particular, we are going to color the edges of the complete graph over the natural numbers as follow. So so assume I is at most j. So we have a pair of edges, an edge which is a pair ij. So we color it with this pair of binary matrices. It's the payoff matrix when you let Si play against Tj, and the payoff matrix when you let Sj play against Ti. Now notice that crucially the number of colors here is finite because it's just a pair of D by D matrices. Here it's really important that we have this bound D on the size of the sets Si and Tj. So there are at most 2 to the 2 times D squared many colors. Yes, so that's what I said. So number of colors is finite. So by Ramsey, we have an infinite monochromatic subset of indices, K1, K2, and so on. And now all is left to do is to interpret what does monochromatic means in this context. So let's do that. So it means that there is a fixed pair of two binary matrices, D by D binary matrices, such that all edges in this infinite set, of indices, have this payoffs. Now, notice that the value of M prime by assumption is less than R, and the value of M prime prime by assumption is larger than R. This is by lemma 1. This is how we got these sets. And therefore, if you have a pair of games, a pair of binary matrices, one has a smaller value than the other, then there must be an entry in M prime, which is 0, where the corresponding entry in M prime prime is 1. Right? Because if you have a matrix that completely dominates another matrix, then also the value of the dominating matrix will be larger. Right? So there must be a pair of indices, AB, such that M prime of AB is 0, whereas M prime prime of AB is 1. And then we just set SI to be the 8th strategy in AKI, and TJ to be the bth strategy in BKJ. And this is, again, maybe this needs a meditation, but it's really just to digest the definitions and this gives you the second lemma, and therefore the proof. Yes, so I'll be happy to take questions, but I'm done with the proof and the talk. Thank you.
Yeah, so thanks, Shay, for this very clear talk. So can you go back one slide, please?
Of course.
Yeah, just to make sure I understand. So this SI and TJs, these are like pure strategies, or this was a bit confusing.
Yes. So you have so we have these SIs, and then we S1, S2, and so on, T1, T2. These are subsets of size D of pure strategies. The SIs are mini strategies, and the TJs are sets of max strategies. And then we find this monochromatic infinite set. So what does it mean? It means that if you look at the payoff of SKI and SKJ, so all the payoffs, yeah, it's a bit hard to, do you see my mouse?
Yes.
Okay, good. So so the point is that if you only restrict yourself to SIs and TJs, which are indexed by K1, K2, and so on, and you look at this vector of payoff matrices, then all of these vectors are the same. Right? So if you let SK1 play against TK2, or you let SK1 play against TK3, you get the same payoff matrix as the binary matrix. It will be the same. So you have, right? So basically these infinite sequences of games they all have the same binary payoff matrices, depending on who plays first, right? On whether I is smaller than J and then we let M prime and M prime prime be this pair of binary matrices that describe all of these games. And we know that the value of M prime is less than R, and the value of M prime prime is larger than R. And then there is another simple argument saying that there must be an entry where M prime is smaller than M prime prime. But smaller means that this one is 0 and the other one is 1, because it's all binary. And hence, if you take the 8th row against the bth column in each of these games, you get a 0 and 1 according to or 1 and 0, depending on who is larger. I'm not sure if this was helpful, but
Thank you. More questions to Shay? If not, yeah, let's thank Shay again.
okay, thank you.
So let's have a 10-minute break.